Okay, so we're going to start looking at Module 3 tonight. As we look at Module 3, I'm going to go into our learning plan. You'll notice here that we're going to be looking at section 2.3 in our book. And then you're going to notice that we are going to be doing the following sample problems or our practice problems. So we're going to be doing 2.4, 2.5, and 2.6 for this module. And then we're going to have some application problems associated with it. So I'm going to pull up our PowerPoint presentation, scooch this over. And we are going to get started here. So as you look at page 36, this is going to be the section in our book that we're looking at. We're going to be focusing now on the relationship between forces acting on a particle, but they are going to be in what we call the state of equilibrium. That means that all the forces are equal to 0. Okay, so as you know, we were using some of the forces and the y was equal to the resultant y component. This time we are going to set some of the forces in the x equals 0 and some of the forces in the y equals 0, recognizing that we are in equilibrium. Okay. Now, we've already talked about vectors, so we're going to continue to represent our forces with vectors. So it's going to be a line with an arrowhead that's going to be fully defined by magnitude and direction, just like we have been doing up until this point. Scalar quantities, on the other hand, only require one thing, but vectors, they require two. So if it is at an angle, we have to make sure that we are representing that, and we're also solving for whatever the direction is. Now, when the resultant of all the forces acting on a particle is 0, it is said to be in equilibrium. We can have two states of equilibrium. We can have equilibrium when we are at rest or in a static state, hence the name of our class here. Or we could have equilibrium when we are moving, but we would be moving then at a constant rate so that we wouldn't have we wouldn't have any acceleration. We wouldn't be feeling that speeding up or slowing down. We would just be going at a constant rate. That is considered dynamic equilibrium, okay? In statics class, we're just going to talk about things that are at rest, so we're going to be in static equilibrium. Now, equilibrium of a particle. So as we look at this particle, and we look at point A, all it just means is we're not looking at a big body of something. We're just looking, just kind of at that smaller level. But we can get the same relationships and the same points across. As you can see here, going up and to the right, there is a 100-pound force acting on that particle. At the very same time, there's another 100-pound force along the same line of action, but going in the opposite direction because of their balancing effect, okay? And if we would identify, for instance, the one going up and to the right as being in a positive direction, because it's 180 degrees exactly in the opposite direction, the other one would be considered negative. And if we add a positive 100 to a negative 100, what do we get? 0, right? And when we have a condition of our resultant forces equals 0, that's a state of equilibrium, okay? So in its kind of simple sense here. Now, we can have multiple forces acting on a particle, and we want to then maybe solve for usually an unknown force based on the fact that we know that this system of forces is in equilibrium. So then that's when we can set our forces in the x equals 0, forces in the y equals 0, and then solve for any unknowns, all right? So this time we're not going to be solving for resultants. We're going to be solving for unknown variables based on the fact that we're giving the condition of static equilibrium, okay? And then these are the two forces or the two equations of equilibrium that we'll be using, and we'll be talking about that and applying that. Now, when we get started with any one of our problems, we need to draw a free body diagram. And we've really kind of started doing that already. We maybe didn't call it that, but anytime that you identify anything pictorial or graphical from the problem that you get in a simplified view is called a free body diagram. So for instance, we have this load of lumber, it looks like, coming off of this truck. We've got two people that are at the bottom, and they're going to try to lift it over these pulleys. We want to maybe a problem statement might be, we want to determine what the tension in those cables are. So we would know how much each person would have to pull down with, okay, in order to lift that lumber, off of the truck. And so for a couple of reasons, first of all, is it a reasonable amount of force that somebody could actually pull down with? And then secondly, do we have the appropriate size cables or ropes that are going to be able to hold that? So understanding the forces that are there and that's acting, that's a statics problem, okay? So drawing then in a simplified version of what we have here. So in this case, we would draw a free body diagram of, if you would, these three, the 3 points or the 3 ropes coming together. First, that are going down to hold up the load, and then second, going over the pulley C and down, and then third, going over pulley B and down. And as we look at our next slide here, this shows us what we would call a free body diagram. It's a diagram just of where those 3 forces come together, represented along their lines of action, which would be along the ropes or the cables that are being used here. And we would try to find then what we call the tension in each one of those. So you'll notice that they're calling it TAB. TAC, and then the load that's going straight down would be the weight of whatever they were lifting. That bundle of wood is what it looked like. Okay, so we're going to practice making good free body diagrams and then accurately representing what we have. So the first problem that we're going to be doing is going to be sample problem 2.4 in your book, and that's found on page 61. Okay. And if we look at the problem that we see here, it says in a ship unloading operation, a 3,500-pound automobile is supported by a cable. The rope to the cable, the rope is tied to the cable and pulled to center the automobile over its intended position. So you're going to notice that there is this rope coming here. There is a person that is pulling on it at a 30-degree angle from horizontal. And they want to know, what is the tension in the rope? Okay, what's the tension in the rope? So what we're going to do is we're going to start by drawing a free body diagram, and we're going to focus on point A, because that's where the 3, if you would, cable and rope come together. Okay, so I am going to go underneath my camera here, and this is going to be our first practice problem, if you would, that we're going to be working on. So we'll solve this one together. So this is sample problem 2.4. Okay. Now, for all of our problems, ones that we had in module 2, the ones we have in module 3, and going forward, every one of the problems that you hand into me are going to have the convention. Okay. And the convention is always going to tell us what is positive and or negative. Okay. So we are going to put our convention in the upper right-hand corner of every problem that we do. Now, I always put a little color on mine because I think it makes it look happier. But as long as you have the vertical and the horizontal going to the right and up arrows, and then a positive symbol here. This is going to be the convention, we call it. Okay. Now, we are going to now draw the free body diagram of that point A. Okay, so I'm going to start by just drawing. Now, remember, I am going to always draw my free body diagrams nice and big. I expect you guys to do the same. If you make it literally a third to a half of the top of your page, that is good, because you have to add all of the labels and such that we have here. And there's angles and stuff like that. Okay. This is going to be my positive Y. It's going to be positive X. And this is going to be step 1, free body diagram, FBD. Okay. Now we're going to draw, the middle here is going to be point A. I'm not going to label that point A. That's going to be kind of assumed, just because there's not going to be room to put A there. So we're just going to kind of leave it. And the center of that is going to be our point A. Now, as we look at our problem, okay, A is in the center here of those 3 cables, and coming straight down is the weight of that car. And it told us in the problem statement that was 35 pounds or 3,500 pounds. So what I'm going to do is, coming straight from the center there is going to be a vertical force going down, and it is the weight of that car. And we know that to be 3,500 pounds. Okay. As we look back, another cable that we have coming is the one that the person is holding. This is at a 30-degree angle from horizontal going, 30 degrees down. So what I'm going to do is I'm going to draw this at about a 30-degree angle. I don't know what the length of it is because this is going to be one of the forces that we have to solve for, but I do know that it's being pulled away by that person. And this is a 30-degree angle. And this is what they're referring to as the tension in cable going from A, which is the center here, down to C, which is identified as the point where the person is holding it. Okay. And then the third cable that is being connected at point A here is the one that is going up to point B. So that's going to be the tension in point B. Now, there is a 2-degree angle from vertical here. So that means it's the 2-degree angle here. So it's a pretty steep. Something like that. So that's going to be going up and to the left, just to the left of our Y. And this is going to be TAB. And then this is the angle that's given to us. This is 2 degrees. Okay. Now, those are all of the cables coming from point A. So we have it represented and we have 2 unknowns here. We want to know what the tension in AB is and what the tension in AC is. So you could even put over here too, you could say find TAC and TAB. Okay, that way you kind of know where you're going, right? I'm doing it in pencil, so it's easier for you guys to read in the class here because I know the projector isn't so great, so I'm a little nervous. I usually have to erase at some point. So I don't encourage you guys to do, I want you guys to use pencil because then you can erase if you make a mistake. I'm just doing the pen because I want you to be able to see what I'm doing. I think it's more clear. Okay, so now what do you think our next step is to do? What have we always been doing? If there's any forces that do not lie on the X and Y axis, what do we want to do? Break them into their components. Yes, exactly. So we are going to draw the components of TAC and TAB on our diagram. So you can do your little construction lines going over, and I just slightly offset so I can physically see that there's another force there. When it shares the same, you would axis as something else. And then make sure that you label them. So TACX, TACY, and then you'll have the same thing for TAB. So make sure you draw them and label each one. And that's where making a nice big diagram helps out a lot. Okay. So now that I have my components in place, I need to now solve for them, right? I need to solve for them. So my step number 2 here is going to be components. Very similar to what we did for resultants, right? So again, we're not finding the resultant here. We're finding the 2 unknown quantities that we have. What are the tensions along those cables? All right. We're anticipating we're going to be using those 2 equations of equilibrium, which are some of the forces in the X, some of the force in the Y. That's why we want to get these all on the X and Y axes. So the first one I'm gonna do is going to be my TABX. And that's going to be equal to, now I'm given the 2 degrees. It's totally up to you. Some people like to have the cosines with the X's and the sines with the Y. If that's the case, then what you need to do is you need to subtract 2 degrees from 90 and use this angle here, which would be 88 degrees, right? So you could do the cosine of 88, or for the X, it would be the side opposite, right? Equivalent, it would be the sine of 2 degrees. Either one. I'm going to go with the sine of 2 degrees just because I like to use information that is available to me. So it's sine of 2 degrees times TAB, which is the hypotenuse. We don't know the magnitude of the hypotenuse. So we are going to put our X component here in terms of the hypotenuse, okay? So our TABX is going to be equal to, and I'm going to find the decimal equivalent of 2 sine. So 0.0349 TAB. Okay, and I'm just going to put a little line underneath that because I'm probably going to need to refer to that, or a little cloud if you want to do that, because that's kind of fun. Then what I'm going to do is over on the right-hand side here, since I'm on TAB, I'm going to do the y component. So since I use the sine of 2 degrees here, I'm going to use the cosine of 2 degrees times TAB. But again, you can also use the sine of 88 degrees, right? We'll get the same answer. So TABY. Okay. And then you're going to do the very same thing, but using the other angle, this time 30 degrees for TAC. So you want to get the X and the Y components. TACX. This one's going to be cosine of 30 times TAC. Everybody doing okay virtually? Just want to be sure.
Yep.
I'm always assuming no news is good news. All good. Thank you, Gabrielle. Okay. All right. So once we have our X and Y components, we can now use the equations of equilibrium. Okay, so the 2 equations of equilibrium that we're going to have here are going to be sum of the forces in the X equals 0 and sum of the forces in the Y is going to be equal to 0. Okay, so that's going to be our next step. I like to say equations of equilibrium. Okay, I always like to know the steps I'm taking. This is our 3rd step. So we've got 2 of them, like I said. So let's start with sum the forces in the X equals 0, and let's see how far we can get, okay? Zoom in a little bit. So we're going to sum our forces in the X equal to 0. You have to write this, and you have to put it in the form that I have here. Capital sigma is the universal symbol used in engineering to sum things, okay? We're summing our forces, so capital sigma. Capital F saying we're going to sum our forces, and sub X means we're in the X direction. And then you're going to have the equal sign equal to 0. That is the equation of equilibrium. It needs an equal sign. It needs 2 sides, okay? So on the left-hand side, we're going to do our sum of our forces in the X. So we're going to go back up to our illustration here, and we're only going to look on the X-axis, okay? So as I go from left to right here, I've got TABX. It's going to the left. It's pointing to the left. That means that it's negative. So I'm going to go negative TABX, okay? And it's negative because the convention that I said at the beginning of my problem in the upper right-hand corner tells me that things going to the right are positive. Then you're going to notice that I have another force on the X-axis. That's TACX. That's going to the right. So that's a positive value. So positive TACX. Now, this is why we don't put positives and negatives in the components. We just put their absolute value because up here, we're going to get our positives and negatives. I don't want anybody to get confused where if they put a negative here and then put it as a negative, that it becomes a positive, okay? So only put your positives and negatives when you're summing your forces either on the X or the Y. All right, so then as we look back up here, there's only 2 forces on the X-axis. So these are the only 2 forces that we are summing in the X direction. You now finish. This is another equation. The next line is another equation. We set this equal to 0. If you don't do that, it will be points off. This is an equation of equilibrium. It has to have an equal, it has to have an equal sign, and it has to have two sides. Okay. Don't like add it in, you know, 2 steps down. All right. Okay. Now what we're going to do is we're going to then substitute the values for each one of these from what we had gotten up on top. Okay. So for TAB, we got 0.0349 TAB. So this is going to be a minus 0.0349 TAB. So we're putting the X in terms of its hypotenuse. We are ultimately going to want to know what the hypotenuse is because that's the tension along that cable. Plus TACX is 0.866 TAC. And then we're going to set that equal to 0. Now, this is as far as we can go. We've got one equation with 2 unknowns. We can't solve for this, right? So what we're going to do is we're going to try our other equation of equilibrium, which is going to be summing the forces in the y direction, okay, equal to 0. So just below here. So I'm just going to put a little cloud around here. We're going to come back to this, all right? The next step is going to be we're going to sum our forces in the y direction equal to 0. You always have to write this. Sum with that symbol, capital F sub y is equal to 0. It's like telling me what you're going to do. All right, then I know immediately below that's what's going to happen. Don't just start writing out things. You have to like logically write, you know, tell me what you're going to do so I can follow along. And then just below here, now I'm going to go back up to my diagram and I'm going to look along my y-axis, okay? So the first force I'm going to be putting up here is going to be a positive TABY because it's going up. Okay. Then I'm going to have a negative TACY because it's going down. And then don't forget, we've got another negatively directed force that's the 3,500 pounds. So those are all 3 of those are on the sum of the forces in the y side, okay? So negative 3,500, and don't forget the units in all phases of the problem. Make sure you put pounds in there for the 3,500. And then now we're going to set this equal to 0. So again, sum of the forces in the y on the left-hand side equal to 0. And now we're going to substitute their values in terms of their hypotenuse. So the TABY is equal to 0.9994 TAB. I didn't round that one. You might say, why didn't you just put it to 1? I don't know. I felt like, again, in the problem, I like to hold 4 and 5 decimal places and then round at the end, okay? And then I'm going to have my TACY, which is 0.5 TAC. And then minus 3,500 is equal to 0. Now, here again, we've got 2 unknowns, TAB and TAC. But now what do we have? We've got 2 equations with the same 2 unknowns, so we can do the substitution method, right? Yeah, absolutely. So that's what we're going to do the work on the next page. Now, how you approach this can be different, meaning whether you solve for a TAB first or TAC first, it really doesn't matter. You'll end up with the same result in the end. So I'm just going to show you how I would approach it. So first, what I'm going to do is I'm going to identify this equation as my number 1 and this equation as my number 2. Number 1, just because it was the first one. Number 2, just because it was the second one. That's it. And then what I usually do is I know that I'm going to have to rearrange one of the equations in terms of one of the variables in terms of the other. So that means that I try to look, are either one of these easier to work with? And I'm just going to say number 1, only because it has one less number to deal with. They're really, neither one of them I don't think is really hard to deal with, but sometimes one is maybe you feel like, I don't know, I'd rather work with that one first. So I'm going to go ahead and I'm going to work with equation number 1 first, and I'm going to solve for one of the variables in terms of the other. But since I'm on a new piece of paper, I'm just going to rewrite my equation number 1 right here. So it's negative 0.0349 TAB plus 0.866 TAC is equal to 0. Okay. So now I just want to get one of these variables on the left-hand side. Since this is a negative value, I'm going to add it to both sides. And I'm going to send it to the other side. So I'm going to have 0.866 TAC on the left is going to be equal to 0.0349 TAB. Okay. And then now, since TAC is on the left-hand side, again, I'm just randomly picking this. You could solve for TAB if you wanted to. If you're like, I really like TAB, and since they're before C in the alphabet, maybe I want to do that one first. Doesn't matter. Okay, it doesn't matter. So I'm going to divide both sides here by 0.866 to solve for TAC. And I am going to get you get 0.0403. Okay. All right. So we still have two unknowns, but now we have one of the variables, TAC, solved in terms of the other. Okay. In terms of TAB. Okay. So we're going to let that one sit here a little bit, and then we're going to go to the other equation, number 2. Okay. So number 2, as you know, was right here. Okay, so I'm just going to rewrite it in that form so we have it all on the same page. If you want to keep yours where it's at, that's totally fine. And then I'm going to move my 3,500 to the other side right away. So equals 3,500 pounds. It becomes positive on the other side. That's all that I did there. Okay. Now, this is where, now that I've got TAC in terms of AB, wherever I see TAC in this equation, number 2, instead of TAC, I'm going to substitute 0.0403 TAB. So 0.9994 TAB minus 0.5 times, now this value, 0.0403 TAB is equal to 3,500 pounds. Make sure you're putting the units in there all the time. Now we want to distribute 0.9994 TAB minus So now we have two terms that we can combine, right? So we're going to take 0.9994 minus 0.0215. So we should get 0.97925 TAB is equal to 3,500 pounds. Notice we now have just one unknown that we can solve for. And then we can divide both sides by 0.97925. So TAB would be 3,574 pounds. Which is the answer. What are they getting here? Everybody get 3,574? Oh, you did. Great. Yeah, you will. Now, something I want to call to your attention that this book does, and some people have already gotten this. So when I look at the sample problem in the book, TAB is 3,570. This book rounds to 3 significant digits, not 3 decimals, 3 significant digits. So 3 significant digits starting on the left-hand side is going to be 357, right? And then that next one, they'll either round up or round down. Since this was 374, they rounded down and they gave their answer as 370. When I give you the answers for the problems at the end of the chapter, I always give them to you from what the book gave. Okay, so they round to 3 significant digits in their final answer. So just know that you can still leave this term just like this. And as long as yours rounds to the 3 significant digits that they have, you're good. And I'll correct it and I'll know. Okay, so just so that you're aware of that. So if you've noticed that you're like, oh my gosh, mine is off, it's not probably, it's just that it's not rounded to 3 significant digits. You're more accurate. Okay. All right. So that is the first cable that we needed to find. So this was TAB. That was one of them that we needed to find, which is how much tension is in that cable going up over pulley B. Okay. Now we've got to solve for AC. Okay. So now that we know what TAB is, right up here, remember in equation 1 where we solved for TAC in terms of AB or TAB, now we can put that TAB right back up in there. Okay. So we can't put this into the same equation because we solved this using number 2. We have to put it back up into number 1. But since we rearrange this here, we can say TAC is equal to 0.0403. And then it's going to be times 3574 pounds. Make sure you put the units in here. And that's going to be that number right there. So our TAC going to be 144 pounds. And that's what they got as well. And that's to 3 significant digits. So 144.03. And make sure you put your units in your final answer. I want to see it in the problem. That way, if they cancel out, you can see why they cancel out. But in this case, it sticks in there, but you get the right units for force. Units for force in the English system are pounds. All right, so that's the second one. So then we solved for the tensions in those 2 cables. And now with that information, we make sure that we have the right size cable and that it makes sense for, you know, maybe in this case, that person who is trying to pull it over. Is it a number that they can actually work with? Is that something that's reasonable to do? So, so questions on that one. So kind of similar to resultant stuff, but a little different. It's this, and the real key here is recognizing equilibrium, using these 2 equations of equilibrium, some of the forces in the x equals 0, some of the forces in the y equals 0, and then, you know, solving for, in this case, we were able to use a substitution method to solve for any unknowns. All right. Any questions on that one? Good. So
I have a question.
Go ahead.
When we're doing all of the components, do you want us to simplify right away? For example, for like the tab of x equals sine of 2 to the of tab, TAB. Could we
Okay.
just leave it as sine of 2 of TAB instead of the 0.0349 TAB?
And then you would leave that in all of these here too?
Yeah, until the very end when we're actually getting the actual value.
Yeah, I think you could. That would be fine. Yeah, you should end up with the same thing. I just think they're easier to combine, you know, as you're doing different elements. Yeah. Yeah, you would just have to put the decimals in, you know, later than earlier. It's up, I mean, I think it's a personal preference. You would end up with the same value. That's okay. Other questions? All right. All right. Okay. Then what I'm going to do is I'm going to stop the recording here and I'm going to start it again for our next sample problem. That way, if you need to go back and look at it, it's kind of easier to find along the way.